Good morning, everyone. Today we're going to continue with our investigation of those special consequences of special relativities. Now, one of those concepts that we have mentioned multiple times before is the fact that nothing can go faster than the speed of light. So if you have a flashlight, the beam of light will always travel at the same speed, which is at 3 times 10 to the 8 meter per second. That's 300 million meter per second, fast enough to go around the world almost 8 times in 1 second. Now that is not just the speed of light, that is also the speed limit of anything that we have ever created. That means even if we create the fastest rocket that we could ever do in the future, that rocket is going to be bound by the speed of light. Nothing that has mass can travel at the speed of light. Because if you remember from the last lesson, what happened when an object travels close to the speed of light is that its mass is going to increase. If its mass is going to increase, then it's going to be more difficult for you to speed it up even faster, which makes it impossible to reach the speed of light because the object will reach the mass of infinity at that point, right? And you won't have enough energy to accelerate something that is already very, very, very massive. Now, but then what happened when you have to add relative speeds together though? So for example, let's look at these two people. Now, we have two observers, one holding an object and is in a vehicle that's moving at, let's say, 50 meters per second. Now, the other person is sitting on the ground. So let's say this person on the vehicle is trying to throw that ball and he's going to release the ball. And now, according to who you ask, they're going to think that the ball is traveling at different speed. So for example, the observer, let's say the observer said, hey, I'm throwing, the observer in the car, right, is throwing this ball at 20 meters per second. Now, what would the observer on the ground measure as the speed of the ball? Well, I mean, obviously, it should be the addition of the two, right? Because, the ball will have the speed of the ball will have the speed from the car in addition to its own speed. So the observer on the ground is going to say that the ball is moving at 70 meters per second instead of 20 meters per second, right? Now, so this math makes sense. Now, but that's the problem though. Look at this picture down below. So now we have a rocket that's traveling really, really fast at 80% of speed of light. And we also have a person who is going to launch, let's say, a rocket, right? So a little, missile. So this missile right here. Now, this missile is traveling at, let's say, according to the observer, who is actually on the rocket, is traveling at 50% of speed of light. Now, this is the measurement according to the observer who's with the rocket. Well, then how fast will the other observer, who is on the ground, think the rocket is, the missile is traveling at? If we use the same logic that we used earlier, we should be adding these two together, which is going to make it 1.3 c, which is what? 130% of speed of light. Right, 130% of speed of light. But that is impossible. Nothing that has mass, now the missile obviously have mass, nothing that has mass can travel faster than the speed of light. So that means we can't just add those two speeds together. If we do, the object will have a speed that's observable by some observer to be faster than the speed of light. And that is impossible. Okay, now let's make that law really, really clear up here. No object can travel faster than the speed of light. There is this wall impenetrable by any object that has mass. So you can either have things that travels at the speed of light, which so far we only know one object in our universe does that, which is objects that are massless. So you can have objects that travel at the speed of light, but that object has to have a mass of 0. It has to be massless, and the only thing that we know that are massless is photon, the particles of light. Not proton, right? Photons. Now, anything that has a mass, anything which mean proton, electron, neutron, things that make up me and you and the rest of the universe, we do have mass. Our mass is not zero. Anything that has mass can only travel below the speed of light. Below the speed of light. So it's either you travel below the speed of light, or you travel at the speed of light if you're massless. Well, we are not massless, so we always travel below the speed of light. So we can accelerate anything so that it crosses the barrier of the speed of light. Okay, so that's the rule. Well, then how do we solve this problem? So in slow speed, we can add the two together, but it looks like in very fast speed, we can't. So when the speed is approaching the speed of light or going over the speed of light, that makes that's kind of breaks our logic. Okay, so now here's another example in a relatively mathematical form. So what happened is there's a kid, right? So in this picture, there's a kid who is on a sled carried by his father, and the speed of the sled is 1 meter per second. And then the kid is throwing a rock to another observer. So a slow ball, which is traveling at 1.5 meter per second according to her. So how fast will the observer think the slow ball is traveling? Now the observer thinks the slow ball is traveling at 1 meter per second plus 1.5 meter per second. So in this case, so when you have classic velocity addition, that means if things are moving slow enough, then we can use this rule. Now in this situation, V is the velocity of the sled relative to Earth. That means the velocity of the two observers relative to each other. U is the velocity of the speed, U prime, right now. So we have this little symbol called U prime, which is over here too. So U prime is the speed of the slow ball, is speed according to the observer that's actually with the object that is thrown. Whereas U is the speed of the object relative to someone else who is observing from the outside. So they're all speed. V, U prime, and U are all speed. Okay, so in picture 1, right? So what happened is the speed observed by the stationary observer is going to be the speed of the sled, which is the frame of reference, plus the speed of the slow ball, which is also moving to the right-hand side. Now the direction matters in here. They both move to the right-hand side, so we add them. So which will be 2.5 meter per second, quite easily. And now the second picture, you see the kids throwing the ball backwards. So in this case, the observed speed will be 1 meter per second, which is going to the right, minus 1.5 meter per second, because this other object is moving to the left, right? So it's a negative. So the reason why it's negative is because that object is moving to the left. So when you add them together, you're going to get negative 0.5 meter per second. So this math makes sense, hopefully. Now, but what happened when the objects are traveling really, really fast? For example, in this case, let's say you have a car that's moving at some speed, and then there's a flashlight in front of it. It turns on the headlight, and the headlight is moving at the speed of light. So, and then the person will also observe that the headlight is moving at the speed of light. Because remember, from one of the experiment that we talked about earlier, speed of light, from the Michaels and Maury experiment, the one that they were trying to prove that there are ether, there's something that Earth is moving against in space, but at the end, didn't work. Speed of light shows no different whichever way you're moving, according to any observer moving at any speed. So this math simply doesn't work, right? So now how do we make a type of math that actually works? So that means it has to be an equation that when the speed is low enough, it works out like the classical case. But when the speed is really, really fast, it has to work somewhat differently. But it has to be an equation that works in like both cases, right? So Einstein developed this equation to adding to speed. So this equation is for you to add speed when the speeds are fast enough so that if you just add them normally, it will go over the speed of light, which then is impossible. Now, if you only look at this equation from the top half, the yellow highlighted part, this is exactly what the classical case is. So what did Einstein actually added then? Well, the part that is being added is this bottom half, which if you look at it closely, it looks quite a lot like the gamma factor, except that it doesn't have a v square on the top and it doesn't have a square root, right? But other than that, it kind of looked like a gamma factor. This equation, of course, is on your formula sheet. Okay, so how does this equation actually work? Now, we can use this in a classical case. So let's say this person, again, observer, holding a ball, and he's going to throw that ball at a speed of, like, let's say 80, right? 80 meter per second. Now, so the speed of the car moving is v. V is the speed of the frame of reference. The speed of the object that's being thrown forward, according to the observer that's actually throwing it, the moving observer, is called u prime. And then the speed that the observer on the ground measure is going to be called u. Now, according to our classical logic, this u should be what? 80 plus 60, which is, so 80 plus 60, which is 140 meter per second, right? It should be that number. Now, does this equation work in that situation? Think about it. Okay, so we can try it. So u is equal to v plus u prime, so which is 60 plus 80. Now, and then we're dividing by this thing, right? So 1 plus 60 times 80 dividing by c squared. Now, but you have to remember though, c is the speed of light. So that's 3 times 10 to the 8 and then square. Okay, so now I don't really have to do this math to tell you that it works, because if you look at this part right here, the highlighted in green part right here, okay, so if you look at that part, this number right here is very, very small. You have 60 times 80 divided by a number that's in the millions square. When you're dividing something by billions and billions of times, the number gets really, really small. So this is very, very small. Okay, very, very small. And very small as in it's very close to zero, right? Very close to zero. Okay, so what happens when you have 1 plus very close to 0? Very close to 1, right? Because you have 1 plus in front of it. Okay, so now what happened to you have 60? What happened when you have 60 plus 80 divided by something that's very close to 1? Well, then you get 60 plus 80, basically. So this is going to be insanely close to 140. So far, this equation works with slow speed, right? So you can try it in a calculator if you don't believe me. 60 times 80 dividing by speed of light square. And then you add 1 to it. And then try to do 60 plus 80 divided by that number. You'll get 140. It's not even going to affect like a decimal point that you can see from your calculator, most likely, right? It's slow enough. So in very, very slow speed, this equation basically reduces back into our classical case. Now, but we're not interested in those situations. We're interested in the situation where we can actually have some funny thing going on, which is adding half a speed of light, for example, to 1 times speed of light doesn't give you 1.5, right? So you want those kind of situation. So exactly, we can look at this. So suppose you have a spaceship that is moving at 50% of speed of light traveling toward the Earth. And it shoots out a laser beam, right? Like in the movie. So the laser beam, of course, moves at the speed of light, according to the observer who is on the rocket, right? So we have 2 observers. So we have an observer who is on a rocket. We also have another observer who is on Earth. So they're different. So observer, so this person is observer 1 and this person is observer 2, right? Observer 1 and observer 2. Now, according, of course, this speed of light is according to the person who is shooting out that laser beam, right? So this speed of light is u prime and is according to the person who's actually releasing that weapon, like shooting that laser beam. So what we want to know is what is the speed that's going to be observed by the observer who is actually on Earth, which is observer number 2, right? So what is going to be the speed observed by observer number 2? Now, the classical case, right? So if we just look at this classically, what would the answer be? Well, the answer is going to be speed of light 1 times plus speed of light 0.5 times, which is 1.5 times the speed of light, which means it's faster than the speed of light, according to observer 2, which we know is impossible. What should the answer be? Remember, speed of light is the same regardless of the observer's motion and regardless of who observes it. So we should actually get speed of light. That means you should be speed of light again, which is really strange. That means we are adding these two together, right? Thinking about it like that. So in the classical case, we are getting, so like 1 times speed of light plus 0.5 times speed of light should, I mean, technically should equals to 1.5 times the speed of light. But we don't want that answer. We know that answer doesn't make sense. What we lead to, what we're trying to get, right, is somehow, some way, we should be getting something like this. 1 times speed of light plus 0.5 times speed of light equals to 1 times speed of light. That's what we actually want to get. Now, because remember, speed of light is the same according to any observer. So according to the observer number 1, who is on the rocket, the laser beam is traveling at the speed of light because it's a beam of laser. But according to the Earth observer, a beam of laser is coming at us, right? It's coming to attack us. So how fast is that laser beam? Well, it's a laser beam, so it should be going at the speed of light. Well, then what about the speed of the ship that is actually housing that gun? Like, that doesn't count? Yep, that doesn't count. So how does that work? Okay, so let's look at, that's actually the genius of the equation that we are using right now. Okay, so now let's label them. Well, actually, we do have everything labeled. So it's u plus v plus mu prime 1 minus v times u prime over c squared, right? So that's the equation that we're going to use. So let's see how that works. So we have 0.5 times the speed of light plus 1 times the speed of light. So plus 1 times the speed of light. And then dividing that by what? So 1 plus, right? So now we have this number down here, which is 0.5 times speed of light multiplied by 1 time speed of light dividing by, well, speed of light squared. Okay, so there's going to be a little bit of algebra that you need to think about. So now c on top right here, that those two c in the equation, right? So c times c is c squared, and then there's a dividing by c squared on the bottom. So these two actually divided, that cancel out with that one, c squared right there. So that's it. And you will have on the top 1.5 times speed of light, so 1.5 c, right? It's like, look at c as x, that way you look at it. And then in the bottom, what do you have? In the bottom, you have this 1 plus 0.5 times 1, which is 0.5, right? 0.5 times 1 is 0.5, which is also 1.5 times the speed of light. Now add 1.5 times, right? So 1.5. So 1.5 times c divided by 1.5. So the 1.5 cancel out, and you get c. Every time, I really wish that we are doing this in class, because every time we arrive at that point, people always go like, whoa. So we just make like 1 plus 0.5 equal to 1. Do you realize that? Like 1c plus 0.5c equals to 1c. So 1 plus 0.5 equal to 1, which your math teacher is going to hate me for this, right? But actually, in relativistic speed addition, this is how it works. Nothing can actually go past the speed of light. So if one of the objects is moving at the speed of light, the other observer will always observe the object to be moving at the speed of light too, no matter how fast the carrier of that first object is, right? So, yep, it works out. So now, let's look at another one. What if nothing in the picture is actually going at the speed of light? Right? I mean, in this case, because the laser beam is actually traveling at the speed of light, so we can actually predict the answer for, so the speed of the laser beam according to the Earth observer is going to be c. We can predict that answer immediately because, well, there's a laser beam. So let's do one that is, slightly different. Now, I apologize because the picture actually, I think at least on my end, didn't come out correctly. So I'm going to redraw that picture. So we have two rockets, right? Rocket B and rocket C. So they're different rockets. Rocket B is traveling slightly slower at 80% of speed of light. Rocket C is traveling at 90% of speed of light. And we also have an observer A who's standing on the ground. He's not even moving. He's Earth in this case. And so what we're going to do is, well, what happened is rocket B tries to launch a missile, right? So this is a missile. So the missile, okay, right here. So the missile is traveling from B to C. Now, according to an observer that is on rocket B, which is this rocket right here, this missile is moving at 20% of speed of light. Now, that is going to be U prime because it's measured from B. Now, the question is, can this missile actually hit that ship in front of it? Can this missile actually catch up to rocket C? Now remember, rocket C is only moving at 90% of speed of light. Now, according to classical physics, right? You look at this, you say, well, okay, so the rocket itself, B, right? B itself is going at 80% of speed of light. And it launches something that's moving at 20% of speed of light. So that means the missile classically should be moving at 100% of speed of light, which is faster than 90% of speed of light. So it will eventually catch up with rocket C, right? So now here's the problem though. That 20% of speed of light speed is only according to the person who is in rocket B. So how fast is that rocket moving, that missile moving, according to a ground observer A though? So according to the ground observer A, how fast is that rocket, that missile actually moving? Okay, so we need to calculate that. So that means is 80% speed of light plus 20% speed of light actually equal to 100% of speed of light? If it is, then that missile will catch up with rocket C. If it's lower than 90% when you add it at the end, then it cannot, right? So here's the situation. So the calculation itself is actually not that bad. I mean, it's exactly like what we have done in the last question. So I'm going to skip through some of the actual math. So 0.8, so 80% speed of light, and we are adding it to 0.2, 20% speed of light. Now, in regular circumstances, if those speeds are really slow, we just add them, right? But because they're moving at the speed of light, and you know that it's impossible for a missile to be moving at the speed of light at the end, right? According to any observer, because the missile actually has mass. Anything that has mass cannot move at the speed of light. So we know that the answer is not 100% speed of light anyways. So dividing by 1 plus, and then we have 0.8 C multiply by, so this is multiply, the one on top is adding, so it's very different, and then divided by C squared. So again, we go through some algebra, things cancels out, and at the end, we get something like this. So it's 1 times the speed of light dividing by 1 plus 0.6. So that part at the end turns out to be 0.6. And if you use a calculator, what is 1 divided by 1.6 is 0.86. So 86% of the speed of light. So that rocket, that missile shot out, that missile from rocket B looks like it's traveling at 20% speed of light according to a person who is on rocket B. But according to someone who is actually outside of that frame of reference, looking at it, that rocket is only moving at 86%. So this time 0.8 plus 0.2 equal to 0.86. Again, another weird way of adding numbers, right? So it's a vehicle that's moving at 80% of speed of light, shooting out a bullet that's traveling at 20% of speed of light according to the person in the vehicle. But the total speed, according to someone who is observing on the outside, is only 86% of speed of light, which means it's slower than the speed of rocket C. So that means the missile will not hit the rocket. It cannot catch up with it. It's slightly slower than rocket C, right? So you can catch up. Pretty interesting, right? Okay, so um, now the next question, so the last question in here is actually pretty easy. So this one, I think if the Earth bomb observers see the question, it will shot directly toward the Earth. Okay, so this one is a very similar question. So I'm not going to spend much time doing the part A. So part A is exactly the same. So now instead of a rocket, what is being shot forward is a canister moving at 75% of speed of light. The ship itself is moving at 50% of speed of light. So, I mean, they're asking you how fast is the canister moving according to the outside observer, right? So that's according to this observer. So what is the speed of the canister according to? So that is exactly the same as the last two example. But what I would do, I guess, is what happened when you shoot that canister backward, right? So in classical physics, that will be negative 25% of speed of light, which means going to the left. But what about in our math, right? So now the only thing that you have to change, which is the beauty of physics all the time, is, things works the way that we expect them to, which is, hey, when an object is moving to the another direction, negative, right? So if the right hand side is positive for you, the left hand side must be negative, then you don't have to change anything in the equations at all. So the equation is v plus u prime, so v plus u prime over 1 plus v times u prime over c squared. And the only thing that's changing in this equation is the fact that u prime is negative. So if u prime is negative, then, well, you just plug in negative value. So it's going to be 0.5, 50% of speed of light. It's going to be minus, because it's going backward, 75% of speed of light. Right, so instead of adding, subtracting, and then dividing by 1 plus 0.5 c multiplied by negative 0.75, so negative 0.75 c. So it's multiplied by a negative value, and then over c squared. Okay, so again, that c squared issue work it out carefully, always cancels out at the end. So you're not actually getting the negative number. So now at the end, if you do this in a calculator, you will get a, now what do we expect again? We expect negative 0.25, right? So what is it right now? We actually going to get 0.04. So 40% of speed of light backward. So leaving the Earth, like 40% of speed of light going backward. Okay. All right. So not a very long class this time. I will write down the assignment numbers. So it's going to be on worksheet number 5. I'll write down those assignment number on the our coursework page and also on the portal site. Okay. All right. That's it for this week. Goodbye.